Your water pressure drops to nothing at 5:47 in the morning, and the sound of that silence, that absence of the hiss you've never once consciously noticed, is the loudest thing you've ever heard. You turn the tap, a gurgle, a cough of air, nothing. The pipes smell faintly metallic, like something tired and old giving up. You stand in your kitchen in the gray pre-dawn light, and for the first time you feel it. Not panic, not yet, just the cold. Clear understanding that everything you depend on runs through a pipe you didn't build, maintained by people you've never met, pressurized by electricity that could cut out before breakfast. You have maybe 3 days of stored water if you're disciplined. Most households don't even have that. The average American home holds less than 72 hours of safe drinking water under normal consumption. 3 days. After that, the biology doesn't care about your preparation plans. Here's what almost no one in the modern world knows. The Nabateans, desert traders who carved a civilization into the rock of the Negev and Jordanian highlands 2,000 years ago, never needed a pipe at all. The modern water system was sold to you as infrastructure. What it actually is a single point of failure dressed up in concrete and chlorine. Municipal water treatment plants in the United States serve an average of 52,000 people per facility. One pump failure, Damban, one cyber attack on a SCADA control system, the industrial software that runs most water utilities. One extended power outage, and that entire population is drinking from whatever they can find. A 2021 report from the Environmental Protection Agency estimated that over $2.2 trillion in water infrastructure investment is needed over the next 2 decades just to maintain current service. That money isn't coming. The system isn't failing in the future. It's already under strain. You didn't build this fragility, but you're the one who will feel it. You were handed dependence and told it was convenience. The Nabateans understood something that took modern atmospheric scientists until the 20th century to properly quantify. Between 200 BCE and 100 CE, they built thousands of stone mounds across the desert highlands of what is now Israel and Jordan, not as burial markers, not as boundary posts, but as water collectors. Each mound was constructed from rough, uncemented limestone rubble, deliberately porous, deliberately dark, and deliberately positioned on north-facing slopes. They were harvesting dew. Not rain, not groundwater. Dew, pulled from air that looked to any outsider bone dry. Archaeologists excavating these sites found channel systems leading from the base of each mound directly into cisterns. The Nabateans were running water from thin air, at scale, in one of the driest inhabited regions on Earth. The air around you right now is carrying water. Not as a forecast, not as a possibility, but as a measurable, extractable physical reality happening in every cubic meter of atmosphere on the planet. Even desert air, which feels as dry as cracked leather, holds water vapor. The scientific measure of how much is called relative humidity, a percentage that describes how much moisture the air contains relative to the maximum it can hold at that temperature. At 30% relative humidity, which is typical of arid highland regions, a single cubic meter of air contains roughly 7 to 9 grams of water. That sounds trivial. Scale it across an open surface over 12 hours of night, and it becomes something you can drink. The key is a principle called the dew point. The key is the ksebu, the specific temperature at which air can no longer hold all the water it contains, and begins releasing it as liquid condensation onto any surface cool enough to trigger that release. Drop a surface below the dew point. And water appears on it, seemingly from nothing. It isn't from nothing. It was there the whole time. Think about a cold glass of water pulled from the refrigerator and set on a table in summer. Within minutes, the outside of the glass is wet. Not from a leak, not from the drink inside, but from the air around it. The surface of the glass dropped below the dew point of the surrounding air, and the moisture the air was carrying had nowhere to go but onto that cold surface. That glass is a dew harvester. A crude one, inefficient, lasting only as long as the glass stays cold. The Nabateans built the same mechanism into stone, and they made it work all night long. Their stone mounds worked because of 2 intersecting principles that modern materials science has since given names to. The first is thermal mass, the ability of a dense material like limestone to absorb heat during the day and release it slowly after sunset. The second is radiative cooling, a natural process in which surfaces lose heat faster than the surrounding air by radiating energy directly into the cold of the night sky, dropping the surface temperature below ambient air temperature without any external power source. A correctly constructed stone surface, on a clear night, can drop 3 to 8 degrees Celsius below the air around it purely through radiation. That drop is often enough to cross the dew point threshold. I add surface wettability, the tendency of rough, slightly alkaline stone to attract and hold water molecules. And you have a passive, zero-energy condensation engine that runs every night as long as the sky is clear. The Nabateans didn't discover a trick. They discovered physics. They just didn't have a word for it yet. To build a functional dew harvester for a single household, you need rough-cut or broken limestone, granite, or dark fieldstone, material that absorbs heat and releases it predictably. You need a shallow collection channel, which can be formed from compacted clay, flexible pond liner, or sealed concrete. You need a storage vessel with a lid, a food-grade barrel, or sealed cistern of at least 50 liters. You need a north-facing or sheltered slope with minimal obstructions above the collection surface to maximize sky exposure for radiative cooling. None of this requires specialized hardware. None of it runs on electricity, and none of it involves moving parts that wear out. Begin by selecting your site. A north-facing slope with a clear view of open sky above, no overhanging trees, no roof overhang, is non-negotiable. The collection surface needs an unobstructed path to the night sky for radiative cooling to function. Clear an area of at least 2 meters by 3 meters and level the base. Next, lay your foundation channel, a shallow V-groove running downslope toward your collection barrel, either cut into compacted earth or formed with clay, sloped at a minimum gradient of 1 centimeter per 30 centimeters of run. Test it with a small amount of water before you build above it. Your third step is stacking the stone. Stack your rubble stone loosely, not mortared, not sealed, in a mound 40 to 60 centimeters high and roughly 1.5 meters in diameter. The gaps between stones are intentional. They increase surface area and allow the mound to act as a thermal battery, absorbing heat all day through its dark mass. Do not use painted or treated stone. Chemical coatings reduce surface wettability and can contaminate your collection. Handle rough limestone edges with gloves during construction. The material is unforgiving on bare hands. For steps 4 through 6, once your mound is built, cap it with a slight central crown so water naturally channels outward and downward to the base. Where it meets your collection groove. This geometry is the difference between a pile of rocks and a working system. Slope matters. Seal the lower 10 centimeters of your collection groove with clay or pond liner, and test for leaks over 24 hours before connecting it to your barrel. Fifth, position your collection barrel at the slope's low point, fully shaded from daytime sun. Heat is the enemy of stored water quality. Fit it with a close seal lid and a simple mesh filter over the inlet, or cut from 100 micron food-safe mesh to exclude debris and insects. Sixth, on the first clear night after construction, lay a single sheet of dark, matte finish plastic across the mound surface. This acts as a condensation amplifier, creating a surface that radiates cooling faster than bare stone and is easier to clean. Weighted at the edges with small stones, it adds roughly 30 to 40% to your overnight yield in the early weeks while your stone mound weathers to peak thermal performance. Under tested field conditions documented in peer-reviewed atmospheric research, a well-sited passive dew harvester of 4 to 6 square meters of collection surface yields between 0.2 and 0.6 liters of water per square meter per night in semi-arid conditions with relative humidity above 40%. A 6 square meter system therefore produces between 1.2 and 3.6 liters per night, enough to extend survival time significantly in a grid-down scenario, and enough to supply drinking water for one adult for 1 to 3 days per collection cycle, without a single external input. Clear, calm nights produce the highest yields. Cloud cover suppresses radiative cooling and reduces output to near zero. The system is seasonal and weather dependent. But it works when it works without any external input at all. A basic household dew harvester costs between $40 and $120 in materials, depending on whether your stone is sourced locally or purchased. You compare that to a 55-gallon emergency water barrel, which runs $80 to $150, holds a fixed supply that depletes and cannot replenish itself, and contributes nothing after it's empty. A commercial atmospheric water generator, the plug-in electric version sold in prepper markets, starts at $300 and requires continuous power to operate. Your dew harvester costs less, requires no power, produces no waste, and improves over time as the stone weathers. The only investment it demands is one afternoon of physical work and the willingness to learn a geometry the Nabateans mastered before the Roman Empire reached its peak. The Wuppertal Institute for Climate, Environment, and Energy, alongside researchers at the University of Oldenburg, has documented passive dew collection systems operating across arid regions of Morocco, Chile, and the Atacama Desert, some of the driest terrain on the planet. Their findings confirm yields consistent with the ancient designs, small by municipal standards, enormous by survival standards. The International Dew Utilization Group, a research consortium that has studied atmospheric water harvesting since 1998, has validated that radiative cooling-based condensation collectors function reliably down to 35% relative humidity, drier than most desert nights in inhabited regions. This isn't fringe science. It's published, peer-reviewed, and field-tested across 4 continents. Water infrastructure in the United States serves over 300 million people through a network the American Society of Civil Engineers has rated D+, a system running on borrowed time and deferred maintenance. When it breaks, it doesn't warn you. It just stops. And the gap between what most households store and what they actually need is measured in days, not weeks. You can wait for the pipe to hold, or you can pull water from the air that surrounds you right now. The Nabateans built that choice into stone 2,000 years ago. You can build it this weekend. Depend on the system or build around it. Your move.